Here I am going to talk about C++ style cast operators, particularly static cast, dynamic cast, reinterpret cast, and constant cast. These are the tools that will help to make your code safer through something called explicit casting. Let us talk them one by one. Static cast. The purpose of this operator is to convert data from one type to another type when the types are related. When I say casting between related types, I mean casting between two numeric types like integer to double, and upcasting and downcasting in the hierarchy of classes. Let us learn this through coding. This keyword, this is used to cast variables of related types, for example numeric type variables or base class and derived class types. Suppose I have, let me comment this out before I use it. Int x equals to 5. I have this integer variable and I have double y equals to, I want to set this variable to x. Now what is happening here is when compiler does this, execute this expression or this statement, compiler actually converts this integer type to double type and actually copies that data into the memory location that is allocated for variable y. This process is called implicit casting. It can help to make the code concise. However, it can be a cause of errors and unexpected behavior, particularly for large size code or large and complex code base. Instead of this implicit casting, explicit casting is a preferred approach. Let me correct this correct character. You can do that explicit casting through this tool, static cast. We can do as follows. Suppose I have a variable y1 and I want to set this to the casted version of x. I want to set this to an expression which is going to be something like this. So we have variable x and I want to cast this to double type. So this is a syntax for doing it. Static cast followed by the angle brackets and double keyword inside the angle brackets, and this is like the function invocation. So this will make the casting appear more explicit and safe, and it helps to spot and understand the programmer's intention and to identify errors more easily. Another example where this this casting can play a role is in function overloading. Suppose I have two functions with the same name, and I have double type, return type, and double type parameters. So these are the two functions, overloaded version of the functions, I mean with the same name. Now if I want to use this function in this way with some integer data, let me put this in a cout statement. And double type data 2.2 and 4, let me use 4.5. So in this case, this first invocation, this expression, this function call will actually go ahead and call this version of the function, because compiler will look into the data type of the arguments passed, and then it will select the corresponding function. And for this function invocation, it will choose this second version of the function. But if I have, let's say, something like this, two and first let me choose the first argument as a double type and the second integer type. In this case, compiler will compiler can implicitly convert this 2.2 to integer and call this function, or compiler also has an option of implicitly converting this x to this add to a double type data and call this function. So there is ambiguity. Compiler cannot determine which function to call. So we can see this ambiguity when we compile this program. Let me do the compilation quickly. So compilation and linking, I think we have a problem here. So this is the same thing. This is the thing it is complaining here. It is complaining this is ambiguous. We are trying to call this function with a double first parameter, first argument, and integer type second argument. So it is ambiguous. Compiler is finding this to be ambiguous. So to resolve this ambiguity, it is helpful to be more explicit about what type of primary you want to pass. For example, if I want this function invocation to call this second version of the function, then I could explicitly cast this to a double type and then call it, and then that problem that we faced just before will get resolved. Let us see. So now it is executing. We don't have any problem here. This is just warning. The warning is that the variable that is actually defined is not used. So I'm going to be I will let me ignore that warning and then execute this program. So now we have this program executed and we don't have any issue with this. So the point is that this static cast can give explicit intention explicitly state the intention of the programmer, so that the programmer actually intends this type to be a double type. Now in addition to this, let me also demonstrate the use of this static cast for upcasting and downcasting. For that, let me clean this up, and I actually want to have a base class. The variable x, and I have print function. It will display the text and value x, and I'm going to have a drive class. It is going to have double type member variable y with data initialized to 2.22. And from the drive class I call the print function of the base class, and also it has the cout statement to display its own text. And value of y. So we have this two classes, base class called base and drive class called derived. So let me have a few lines of code to use this classes. Let me have a base class object called bc and drive class object called dc, and if I call print function through this BC object, and if I call a print function through DC object, what I expect is in the first case it is this function I want to get executed. In the second case I want this function to get executed, and I actually want yeah, I expect that this drive class will actually call the base class version as well. So in the first case there will be one line output base class followed by the value x 20. In the second case it will display both 20 and this line, and followed by 2.22. so let us see to make sure that at least this code is without issue, without problem. So switching to the terminal, and we have compilation and linking. I think there's a problem. Well, I think that I missed a colon to place. I missed to place colon here in this place. So let me go back to the code and fix it. Yeah, it is here. Again to the terminal. So in the first invocation it actually displayed base class followed by 20, and then base class 20 and drive class 2.22. so it is okay. I mean to start talking about this the use of static cast for upcasting and downcasting. So now here if I want to, let me have a text displayed. Just as a marker to separate the lines that's going to be displayed. Now here what I want to do is I want to actually cast this DC into DC.print, but I actually want to cast this DC into the base class. So using static cast, and the way of doing that is and base class. So this is a syntax. This process is called upcasting. This is called this is the process of casting a drive class object to the base class object. So in this case, let us see whether it works or not first. I'm going to be compiling and linking and executing. Looks like it is working, right? The drive class had this information printed, but it was casted to the base class, so base class doesn't need this drive class version. So this was actually avoided, skipped, and then only base class portion of the information was actually displayed there. Right now, if I want to do the reverse casting, something called downcasting, casting from base class to drive class. So I have a base class object BC. I want to cast this to this is actually not possible. If I run this, it will definitely complain. So let me go and see that complaint. So it is already complaining, no matching function for the drive class to base class. So this is oh, yeah, I think this is okay. So this is this kind of casting is not possible here. So let me comment this out. If you want to do that casting, you have to go do that through either reference or through the pointer. So let me do that sort of casting through the reference. Let me create a base reference and BR, and you can use the base class reference to refer to drive class object. So this is a drive class object, and this is base class reference, and this reference is actually set to drive class object. In this case, I can cast this this reference BR to drive class reference and call print function. If I do this, there's not going to be an issue, because this actual object is a drive class object. So you cast, even it is a base class reference, you cast to drive class, and it will become the result of this evaluation will become the drive class reference, and you will be calling this print function through that reference. So we are not going to have issue in this case. And outcome, right? So these two lines are actually displayed by that statement. Now let us go ahead and do the reverse casting. So this is casting from base class to drive class. This is called and I want to do something else. BR2 equals to this is actually referring to, let's say, base class object, and cast it to drive class. This also downcasting. So let's see the output of this statement. So we have these things. One thing to notice here is that that statement displayed these two lines. The base class data was printed correctly, but in the case of drive class it is not printed correctly. This is because the object was base class, but it was casted to drive class. So drive class has its own memory space for its attribute y. So that y value that is set, the data for the y is not defined. So we have something that actually is not defined in this case. Therefore, this kind of casting should be carried out very carefully. Sometimes it may result in undefined behavior. Now we can do this through pointer as well. A base class pointer ptr pointing to drive class, and let me place this marker before this statement here. So we have this without issue. We didn't have any issue here, because actually the pointer was pointing to drive class object. So this pointer was pointing to drive class object. It carried the total information, the base class data and drive class data, so we cast it to drive. We don't have any issue. But if we do the reverse, we will have the same problem like before. Good thing about using pointer is that I can reuse this pointer. I can use the same pointer to point to, let's say, base class object. So in this case, definitely we will see the problem similar to that what happened in this case. So you can see this, I mean, something undefined behavior. Now, dynamic cast. Dynamic cast can be seen as an operator in C++, which can be used to check whether or not the conversion of a dynamic object to another type is possible or successful or not. We have this code to begin with, the base class with attribute x, which will be set to 20 by default, and it has a print function which displays this text followed by the value of this attribute 20. I have a drive class. Let me call this drive 1. So drive class with attribute y, and data set to 2.22, and print function which actually calls the base class version of the print function followed by its own displays its own data text. And I'm going to be having another class called 2, drive 2, and again let me just copy everything from here, and actually the text displayed should be here, drive 1 in this case and drive 2. That will actually distinguish. Let me make it a little bit more visible. So drive dash 1 and drive dash 2, and also this data will actually let me make this data different as well, so which will help to distinguish the printed line. So we have this hierarchy, again base class and drive 1 class from base and drive 2 class from base. Don't forget to have a semicolon at the end of a class definition always. So now to experiment a dynamic polymorphism, I will actually use a pointer, base class pointer, and it is always a safe practice to initialize to null PTR in the beginning. Now if I use this PTR to point to new base class object, I can use this to call a function bptr, the function of the base class print function. We have print function in all base class, drive 1 and drive 2, so we can call that function. And I can have after I use this, because this pointer is pointing to the dynamic memory space, so you need to delete that memory before you want to reuse this pointer to point to another object. And it is now pointing to a new object, drive 1 object, and then again call this, and again delete, and make it point to another object. So here this base class pointer pointing to base class object, and the same pointer pointing to drive class object and another drive class object, and calling print function for this. So first let me make sure that I didn't have problem with this code, and I will discuss it further. So this is a compilation. I think there is a one issue, maybe I missed semicolon somewhere. Yeah, I missed a semicolon in this place. Again, I did miss a semicolon in line 36. So we have line 36 here. So compilation and execution here. So it is displaying this base class, right? So it is not actually displaying what we expected. In the second case, we expected the drive class version of the print function to be executed. In the third case, the again drive class, but the second drive class version of the print function to get executed. So in the first case, I actually wanted in this case, because this is pointing to base object, so I expected this statement to execute this function. Here in this BPTR is pointing to drive one object, so I expected this statement to execute this function, printing this text followed by this text. In the third case here, I expected this function to be executed, but it's not happening. It's actually executing the base class version of the function. So the reason for that is the dynamic polymorphism is not implemented. This print function is not behaving. This print function is behaving. This print function and this print function and this print function. All these executions are behaving. I mean, they are not behaving differently. They don't have a different form. Therefore, this is not a polymorphism implemented. If polymorphism would have been implemented, then this behavior of this function, behavior of this function, and this behavior of this function should be different, because they actually, this pointer actually point to different dynamic object. So to realize that polymorphism, you need to make this print function virtual. So by putting this keyword virtual in the first place, in the first line of the function, you actually we will get the expected behavior. So the behavior of this function will be base class behavior, and here it should be drive one behavior, and in this case it is going to be so let us see whether that happens here or not. This is just a warning. This is a warning which doesn't have any consequence in our case, in the topics I'm explaining here. But this is actually asking me to have a virtual destructor in the base class. So I'm going to be ignoring this for a moment. So now you can see in the first execution, the behavior actually displayed this function, displayed this text. In the second case, it was this thing, these two lines were displayed. In the third case, this two lines displayed. Clearly the behavior of that the statement, that function execution, is different in three cases. So now we have a polymorphic behavior. So the important thing is we need to the purpose of this recording is to discuss dynamic cast. So dynamic cast is used to check whether two objects are same or not. right? For example, if I do something like this here, if I want to cast, because these are dynamic objects, so you can apply dynamic casting here. So if I dynamic cast, I can apply dynamic casting of this object to a different type, drive one type. This is best type, so dynamic casting to drive type using this syntax. This is syntax, and you have angle bracket, and you this is target type, which is and so in this case, this the entire expression will return either a pointer and a valid address or null ptr. If this casting was okay and it did successfully cast, then it will return the valid address of that object, that casted object. Otherwise it will return null ptr. So based on whether this is null ptr or not, you can determine whether the casting was successful or not. So what we can do is, you can put this in if statement. If dynamic cast is not equals to null ptr, then you can display you can use this object to call the function. Else otherwise, so and similarly you can also do that kind of casting for the drive to base class. Let me just copy this lines here, and I want to cast this to, let's say, base class. And in this case I want to experiment casting to drive one type, right? So this is a dynamic object, here is drive two type, so we want to cast to drive one type and see what happens. There's an error print, I think typo problem. So I think it should be the syntax. This is not a typo, this is a syntax problem. So to call because this thing actually returns a pointer, so you need to use this operator to call the member function through the pointer. So in the first case the casting was unsuccessful. That means the casting from base to drive class was not successful, so this text was printed. In the second case it was successful, therefore this was displayed. In the final case it was not successful, right? So let me just copy this and just I'm actually moving this to here. So this was the output we got. So this base class 20 was outcome of this statement. After that casting was unsuccessful. That is, conversion of this base class dynamic object to the drive one was not successful. So and then after that we have this print. from this is drive class object, so I think it should display 2 lines, and after that casting to base class and display. So it actually displayed these 2 lines. Display, right? And then after that we have this drive class displaying these 2 things. Yeah, so this thing. So this was the outcome of this this was outcome of this if statement, and these 2 lines were outcome of this this print function, and these lines were outcome of this function. In this case this was I mean, casting was successful. Casting from drive to base class was successful, therefore we are able to this statement was actually executed, and we didn't have this text printed. So this is the uses of dynamic cast operator. So again let me emphasize it. The purpose of this main purpose of this dynamic casting is to actually see whether conversion to particular type is actually successful or possible or not. Okay, so in this case that is exactly what we are doing here. So we are actually trying to cast it, and if it is successful, then we actually use that object and display. Otherwise we do not use that object, and then we actually display the error message here. Reinterpret cast. Reinterpret cast is mostly used for casting from one pointer type to another pointer type. It is also possible that reinterpret cast can be used to cast from pointers to integers or from integers to pointers, and also it can be used to cast from one reference type to another reference type. Now let us learn reinterpret cast through coding. For example, I have x variable set to value 5, and I have integer pointer pointing to x. So if I want to see this data from the angle of let's say double type, this is integer type data. It is stored in the memory space in a certain way, in a certain bit pattern. But if I have to read that from the double perspective, the meaning of that data or the bit pattern is going to be totally different. So if I want to see that from the double angle, double perspective, or in that case what I can do is by using of course IPTR. In that case I can reinterpret cast using this syntax, and you cast IPTR, but the target cast is going to be double pointer. So now this entire expression will return a double type pointer. If you want to access data, you want to put this asterisk before the pointer, and I can put this in cout statement with some label, and then afterward data. Now before that I want to actually display actual value of x through IPTR. So let's see the output of this code. So you can see in the second case it is not defined, right? So it's kind of not defined because if you try to read this x in the form of double, then the meaning is actually usually maybe not defined. But this is what we see here. But if it happens that, for example, some double type data is stored as an integer, then in that case, for example, the bit pattern that is stored, bit pattern of the data that is stored in the memory space for x, actually that is actually some meaningful double value. In that case, this conversion can be okay, or we'll have some double value displayed here that would make sense to our eyes. Now, if you can also use reinterpret cast to convert cast from, let's say, some integer to address. So you can do it like this: 5 as address, I want to cast to integer type, no, in integer pointer. I want to convert the value to integer, and the value I want to convert into integer is let's say 5 x, and also I also want to see what is the size of, because if you see x, the size of x is going to be 4 byte, but size of address is usually 8 bytes. So from that size you can see that the converted value is actually an address. So we can have size of, let me put this in the next line, inside size of, I'm going to be putting this entire expression. So this is casting integer to address. So you can see the 5, if you cast to the address, it is going to this integer, so it will not change the value. But the size, if you look at the size, it is 8 byte. That means it is actually casted, or presented in the form of an address. Similarly, you can also cast from address to integer. For example, I want to actually see the address of x as an integer. One problem that comes with address of integer is, if you the address actually is 8 bytes, so if you cast this into the 4 byte, then there could be information loss. So if you want to see that address intact, then maybe you have to use the target type, which has the same capacity as this address. So I'm going to be using long in this case, address x. So you can see this address as an integer. This is in the integer form, right? The address would actually this is actually long form, because the text I put integer, but it is actually long form. And one more thing here, so you can also use this conversion to convert from one reference type to another reference type. Suppose we have one integer reference type referring to x variable, but I want to actually cast that type to double type. And as you can expect here, we'll have the same problem that we have I think in this case here. We're casting the pointer to double type, so actually we're trying to read the integer data from the perspective or from the angle of the double type. In this case also we are doing the same. We are reading the integer data from the perspective of the double bit pattern interpretation. So we have the same issue over here. Now constant cast. Constant cast is for removing constantness from a variable. It is useful when you need to pass constant pointer or reference to a function where non-constant one is required. Let's learn it through coding. Here suppose I have a integer set to value 20 and I have integer pointer, constant integer pointer x pointing to w. So the feature of this constant integer pointer is that you can use this pointer to access the data, but you cannot use this pointer to actually modify the data. For example, if I use this pointer to display the data, I can do it like this, but if I try to modify this compiler will actually complain in this line number 9. So now it is complaining this line number 9, this is read only, not modifiable through the pointer. So this is not allowed, but in some cases, in some situations, it may be required for you to be able to make changes even it is a constant pointer. In that case, you can remove that constantness. From the pointer. So you can do that by using constant cast. So this is the syntax for doing it, and the target type is going to be integer pointer. So if you cast like this, and this entire thing will actually return a pointer that allow you to make changes. So putting this asterisk dereferencing, it will give access to the memory space, and then you copy data in that memory space, and after that if you display x, you will see the updated value. So we have updated 30 value over here. This constantness it may be required when you have let's say a function like this. Let's say let me have print function which receives an integer pointer called iptr, and it has a statement, cout statement to display the data, and I also have so these are two functions, print functions, and if I want to these functions actually are designed to receive the pointer as a non-constant. And if I actually call this function with let's say this constant pointer, this x print, and compiler will complain about that, because this whatever logic in which this x is used, that logic is should be designed so that the changes is not allowed through this pointer. But when you have this kind of function, and there could be logic that may be changing the pointer, because this function is designed and without expecting that this pointer can be a constant pointer, that pointer that comes in. So if I compile this in this line, and also if I think in this case, yeah, if I have another function, if I also call that reference version of this um, function. So in 19 and 20, I expect to get the compilation error. So we have this compilation error, printf no matching function or call. So it was constant. So constant is I mean the function with this constant integer pointer is not available. Reference is not available. Also function with constant integer pointer is not available. So to get over this situation, we can use constant cast. So if I do constant casting of this thing, this values, to integer pointer, and also here I think in this case this is a constant pointer, so in this case we can do I think let me have we can also have a constant reference, right? Constant int reference, and let me call this IR equals to W, referring to W. So in this case we can actually constant cast to reference as well, IR, and then so you can also remove constantness of the reference, not only of the pointer. So we have a reference, so we actually want to remove the constantness of the reference. So we have it is working without an issue, displaying the data that is actually correct. Now finally I actually want to demonstrate discuss a situation where we have, let's say, a similar situation for the class, right? For example, I have a class and I have public function called print, which is non constant, and always don't forget to put a semicolon at the end of class definition. And I also have another function print, which actually receives constant version of my class, constant reference MC, and it actually calls MC dot right. In this case what will happen is this is a constant object, so the constant object will always look for a function that is actually query function, something like this. If you don't have this kind of function, then compiler will not find this invocation to be compatible with this function, so binding will not take place. If I create, let me create this object of my class, and I call that print function, passing that object. We'll definitely see a complaint here. So we are getting complaint in line number 18, which is exactly the inside the function, I guess. So let me go back. So this is line of 18, right? So we are getting complex in this place. This is a constant object. We need to, if we remove constantness of this object for this particular purpose, then we should be okay in that case. So we can do that by constant casting this MC object. Reference and like this. So with this it should be okay. This invocation should be okay, and this function call should be okay, and also this print function invocation should be okay. Let's do it. So we have compiled, and this print function executed, and which actually displays this print text. Thank you for watching this video.